The word nitty-gritties means we are going to look at a few details concerned with hypothesis testing. And in today's discussion, I would like to concentrate mainly on the errors which happen in hypothesis testing, the type 1 and type 2 error. We are meeting after a long time. I think it's about 3 weeks gap. So I also don't recall, which examples I discussed and what were the main points made last time. So there may be some repetition, but that's okay. Now, type 1 and type 2 errors, they're always with respect to null hypothesis. So depending on the situation and the problem, we formulate the null hypothesis, which is notated as H0 or H0. And remember always that our goal is to reject the null hypothesis. Okay, we always take the stand that with the help of the data, we would like to reject the null hypothesis. And the methodology has been explained many times that once we have decided the null hypothesis and the confidence interval, okay, then we do something to show that this hypothesis is not consistent with the data. Okay, and since data cannot be falsified, data is right in front of us. Okay, we cannot ignore the data. Therefore, if a hypothesis and data are inconsistent with respect to each other, then we have to reject the hypothesis. We can't reject the data. Okay, data is a reality. So there are two kinds of error, type 1 and type 2, and they're always with respect to null hypothesis. Let's remember this. The null hypothesis is the foremost entity in all this discussion. The errors are also with respect to null hypothesis. Now, 4 situations are possible. The hypothesis is actually true, okay? And the hypothesis is actually false. Hypothesis is either actually true or false. So these are the 2 possibilities on the row. And based on the data, we either accept or reject the hypothesis, which has a very definite mechanism, okay, for accepting or rejecting. Now, if the hypothesis is true and we accept it, then this is a no error situation. If the hypothesis is false and we reject it, this is also a no error situation. Both these are favorable situations. Now, if the hypothesis is true and we reject it, okay, then we have made a mistake. Hypothesis is true and we are rejecting the hypothesis, saying that this is false. Then we are making what is called the type 1 error, okay? And the opposite case is the hypothesis is false and we have accepted it. That is known as the type 2 error, okay? So type 1 error corresponds to the level of significance alpha, and type 2 error corresponds to a notation called beta. Okay, so this is alpha, type 1 is alpha, type 2 is beta. Alpha corresponds to the level of significance, and 1 minus alpha is the confidence interval. Okay, so let's proceed with this discussion. This is a very key matrix for all of us. Let's remember this. The type 1 error appears on the first row, second column, if the first row is that of true hypothesis, which is natural and quite easy to remember. Okay, so true and false, accept, reject. Now, let's remember the confidence interval table, which is very, very useful. This I remember was done last time and maybe last to last time also, and very important for our discussion. So the test types are on the columns: two-tail test, left tail test, and right tail test. And the rows are confidence intervals equivalent to significance level also. So if the confidence interval is 90%, then we are prepared to tolerate an error of 10%. Okay, the significance level is 0.10. 95% confidence interval, significance level is 0.05, 99% 0.01. Now, when we have two-tailed test, then the normal curve is symmetric, and this is a standard normal curve with zero mean and standard deviation 1. So 90% confidence interval would give rise to an error region of area 0.10. And since the curve is symmetric about the zero mean axis, we'll have the critical region starting from plus 1.65 up to infinity and minus 1.65 going to minus infinity. Okay, so I have the standard normal curve, which is bell-shaped. So from 1.65 to infinity and minus 1.65 to infinity, these two regions together will give me an area of 10% or 0.10. Okay, and this is my significance level of significance region. If I have to do a left tail test, okay, less than some quantity, then naturally the critical region has to absorb both sides of the zero mean axis. So naturally the critical point has to move towards zero, covering more area, covering the 0.10 area. I do not have the positive region accessible to me, so it is minus 1.228. And similarly, on the positive side, the critical point also has to move towards zero, so this is 1.28. So 1.65 and minus 1.65 minus 1.28 plus 1.28. Now 95% confidence interval. Here the critical points are minus 1.96 and plus 1.96. The error region on both sides, okay, of the zero mean axis at sum up to 0.05, okay, 0.05, and each error region towards plus infinity and minus infinity contribute 0.025. For the left tail, again the critical point has to move towards zero, so minus 1.65 is the critical point, and 1.65 is the critical point on the positive side. Okay, so 1.65 up to plus infinity will cover an area of 0.05 or 5% area. So it is no coincidence that 1.65 here is identical to 1.65 under two-tail test when the confidence interval is 90%. So for 90% confidence interval, you have to cover 5% and 5% on two sides of the zero mean axis. Okay, so 5% area is covered by z value of 1.65 going up to plus infinity, and therefore when I have to cover 5% area by the right tail or left tail test, naturally I have to cover 5% area either on the positive side completely or negative side completely. That 5% has to be equal to the 5% in the 90% confidence interval also. Okay, and in 90% confidence interval, I could have obtained the area from two sides on the positive region and the negative region. Now only one region is available to me, so this 1.65 appears here again. For 99% confidence interval, the two critical points are minus 2.58 and plus 2.58 for two tail test. And for left tail test, it is minus 2.33. Right tail test is 2.33. Okay, so this is a very useful table in hypothesis testing, as is the other table, which is type 1 and type 2 errors representation by means of this a kind of contingency matrix, which is a 2 by 2 table. So let's remember both these tables. These are important for hypothesis testing and very valuable instruments. Now, the significance of the level of significance alpha. What does this mean? When I have 90% confidence interval, alpha is 0.10. So the intuitive statement corresponding to this is that we are prepared to tolerate 10% of error. And always remember, the significance level alpha is tied closely with the type 1 error. Okay, so confidence interval gives rise to alpha, the level of significance, and alpha is tied intimately with type 1 error, and type 1 error is tied intimately with H0, the null hypothesis. So everything begins with null hypothesis and the confidence level that we have decided for ourselves for operation. Okay, so 10% type 1 error is 10% type 1 error is the correspondence with alpha, the significance level. So the probability of wrong rejection of H naught, okay, if we wrongly reject H naught is supposed to be rejected, okay, supposed to be rejected. And if that rejection is wrong, then 90% confidence interval means that probability of that mistake is 10%. 95% confidence interval where alpha is 0.005 similarly means prepared to tolerate 5% of type 1 error, and probability of wrong rejection of H naught is 5%. 99% confidence interval, alpha is 0.01, prepared to tolerate 1% type 1 error, probability of wrong rejection of H naught is 1%. So with this understanding, let's proceed to more details. As alpha decreases, the test becomes more and more stringent. That is more and more strict and more demanding. So as we constrain alpha, make it smaller and smaller, the error region becomes smaller and smaller. That means our tolerance level also goes down and down. We are prepared to accept less and less amount of error. So let's take a look at the standard normal curve. The zero mean axis is the axis of symmetry. And we know that from plus 2.58 and minus 2.58, these two regions correspond to 1% error. 1.96 and minus 1.96, the two left and right regions, 5% error. Plus 1.28 and minus 1.28, the left and right regions correspond to 10% error region. So everything is with respect to the error region defined by the standard normal curve. Okay, everything is at the backdrop of the standard normal curve. So on the upper right side, it is 1.65. On the lower left side, it is minus 1.65. We'll take an NLP problem, which we have seen before, and we will understand our type 1 and type 2 error in the context of this NLP problem. And I believe this problem was mentioned last time. So we have a named entity tagger, which is given a sequence of 50 words and is asked to identify if the words are name or no name. Okay, so the problem is very clear. I'll look at a sentence, let's say a sequence of 50 words, and my goal is to tag the words as a named entity or not a named entity. Is it a proper noun or not? If the tagger tags 32 words correctly, determine if the results are significant at 10%, 5%, and 1% level of significance. So these questions are statistical questions. Named entity tagger is an NLP problem. Okay, so here statistics and NLP are meeting together. The statistics expertise will come from the data scientist. The named entity tagger expertise will come from NLP and machine learning researcher. Okay, so these two worlds have to interact now. Now, and the question is determine if the results are significant at 10%, 5%, and 1% level of significance. This is the language of statistics and data science. Okay, what is the interpretation in the NLP machine learning world? Okay, so let's see. Now, I have this example. The input sentence is, in the recent address to Congress, the US President Biden had two ladies, Pelosi and Harris, sitting behind him. Okay. In the recent address to the Congress, the US President, I think it is Biden, had two ladies, Pelosi and Harris, sitting beside him. The output that is expected is in is 0, not a name, the is 0, recent is 0, address is 0, to is 0, Congress is a name. So that is why 1. The is 0, US is 1, US is a name, President is 0, not a name, Biden is a name, so 1, had 0, 2, 0, lady 0, Pelosi name, and 0, Harris name, sitting 0, behind 0, him 0, and full stop 0. So this is the expected output, and we have been told from our observation that out of 50 words, 32 words have been correctly tagged this way as name or no name. Somebody please verify that you're seeing the slides.
Yes, sir.
Yes.
Okay. Okay. So this has been done. Okay. Now things are in my hand. This data has come in front of me, and this is my observation. On the face of it, the tagger accuracy as evidence from the data is 32 by 50, which is 64%. Okay, but on this is only one sample. I surely have to do much more sampling, and sampling we know is costly. So first and foremost task is compare with random guessing. Now this is a very typical AI situation. Okay, happens in NLP, speech, computer vision, planning, everywhere this question comes. Okay, if in particular if the accuracy is low. I am sure many of you have experienced this when you have sent papers for reviewing, or when you are testing a system in front of an evaluator. If the accuracy level is low, okay, in particular if the value is close to 50%, then a very natural question to ask is the system doing anything better than random guessing? This question we have encountered so many times in natural language processing. Okay, is the system doing anything better than random guessing? And for random guessing, what is the algorithm? The algorithm is very simple. You perform a random experiment. Okay, so in this particular case, for example, we have two outcomes: a named entity or not a named entity. So I have a very natural algorithm at my disposal. I'll take a coin, I'll toss the coin. Okay, if the head comes, then the word is a name. If I get a tail, then the word is a not a name. Very simple algorithm. The only resource I require is a coin. Okay, so this is my random guessing, and I assume that the coin is a fair coin. So the algorithm is simplicity itself. Okay, head, name, tail, not a name. So is the tagger doing doing random guessing? I'm getting an accuracy of 64%, and I want to rule out the possibility that the tagger is not doing random guessing. It has an actual algorithm underlying it. Okay. So now I formulate the probabilistic analysis setting. The first and foremost task is to define H0, the null hypothesis. Okay, everything starts with H0, and H0 is formulated by an understanding of the problem. Okay, now the doubt in my mind is this named entity tagger, that is named entity indicator, okay, is it doing a random guessing? So if it is doing random guessing, then the probability of every word either being a name or a name, not a name, that tag, one of these two tags, has the probability of 50%. Okay, if the algorithm is a random guessing algorithm with fair coin. So the null hypothesis is that the tagger is actually doing random guessing. Okay, so the probability of success and failure, that is probability of name and no name, is 50%. Okay, so the accuracy of the tagger is 50%. That means the probability of a word being name or not a name is 50%. So this is my null hypothesis. You have to see carefully how, from the knowledge of the problem and the property of the problem, we have been able to crystallize a null hypothesis. Okay, the probability of or the accuracy of the tagger is actually 50%. It is doing random guessing. The probability is 50%. After that, everything will begin. Now the confidence interval also is the parallel entity which is in my hand. This is also a design parameter. The first design parameter is the null hypothesis. The second design parameter is the confidence interval which I am choosing. And I am choosing 90%, 95%, and 99%. Now the process will start and we will observe how the process unfolds. Okay. Since my null hypothesis is p equal to 50%, alternative hypothesis is p greater than 50%. Okay. Again, notice how the alternative hypothesis is formulated as per the problem. I am interested in the named entity identifier accuracy being more than 50%. Okay, less than 50% is of no use to me. So a not equal to null hypothesis is not useful because the negative side is of no interest. Okay, less than 50% accuracy is of no interest. Greater than 50% accuracy is of interest. So since my null hypothesis is greater than 50%, I have to use the one tail test or the greater than test, and which is on the positive side of the zero mean axis. Okay, so the nature of the problem is dictating that I take a greater than test, which is the one tail test. Naturally, my critical point, okay, the critical region now will be appropriately decided. Remember the table of two tail, one tail, and one tail test, and also the type 1, type 2 error table. Okay, so alternative hypothesis p greater than 50%. Now let's begin from null hypothesis. The consequence of null hypothesis, first consequence of this is that the mu, okay, the mean accuracy is n into p. N is the number of samples, 50. P is the probability of success and failure, 0.5. So 50 into 0.5 is 25. So out of 50 words which are tagged by this named entity identifier, if it is using a fair coin for its algorithm and its tosses, then 25 expected number of words which will be correctly tagged is 25. Okay, so the total number of the mean number of correctly tagged words will be 25. So this is the population mean 2 as per the maximum likelihood estimate principle. Okay, so if the accuracy is 0.5, if the named entity identifier is doing random guessing, then out of 50, 25 words are expected to be correct. So every time I take a sample of size 50, okay, and thereby with sufficiently large number of such samples, size is fixed 50, I'll cover the whole population. Okay, and the mean number of correctly tagged words out of a sample of 50 will be 25. Now sigma, which is the standard deviation, also is obtainable from sample size n, p the probability of success 0.5, q the probability of failure 0.5 again, and square root of this. So this is 12.5 square root, which is 3.54. So I have got sigma, I have got mean, which is 25, and by maximum likelihood principle, this 25 and 3.54 is the best I can do with respect to my guess of the mean population mean and population standard deviation. Now I have the sample statistics. I have the population mean and population standard deviation obtained by maximum likelihood principle from the sample. Now I am prepared to take the Z test. Okay, we are still in Z test. T test, F test will follow very easily from Z test with a few assumptions being changed. Okay, so 25 mu and sigma at 3.54. Now we remember these confidence intervals, and now I examine the situation now. Okay. So Z observed is 32 minus 25. I was given the data, 32 out of 50 are correctly tagged. 32 minus 25, population mean is 25 in a sample of 50, divided by 3.54, the sigma, I get the value as 1.98. So from the data, the Z observed is 1.98. I take 90% confidence interval, then ZO is greater than ZC. The critical value ZC is 1.28. 10% of the area um, will be from 1.28 to plus infinity. And we are doing one-sided test. For 95% confidence interval, the critical value of Z is 1.65. Again, ZO is greater than ZC, which is 1.65. For 99% confidence interval, on the other hand, I have the critical value as 2.33. Here, ZO is less than ZC. Okay. So I have got three different critical values of Z depending on the confidence interval I chose. 90% it is 1.28, 95% 1.65, 99% 2.33. What is the implication? And Z observed from the data is 1.98. Now we come to the decision. Okay, now we are in a situation to be able to make the decision. For 90% confidence interval, the decision is H naught is rejected. Okay, because we have entered the rejection region. Okay, 1.98 is greater than 1.28, which is the critical value. So the alpha region, okay, the error region, 1.98 to plus infinity, 1.9 is greater than that. I have entered the rejection region. So H naught will be rejected. So I reject H naught, P equal to 0.5, and accept HA. In other words, the data in conjunction with the confidence interval suggests that the named entity identifier tagger is doing better than random guessing. It is not doing random guessing. It has a proper algorithm underlying it, and it is doing better than random guessing. That is the consequence of the data and the confidence interval we have decided for ourselves. Okay, so what is in our hand after the data is given is the confidence interval. Let's go forward. What does it mean? Implication of 90% confidence interval. So if we are prepared to accept 10% type 1 error, then H naught can be rejected. Okay, so if H naught is rejected, incorrectly reject, if H naught is rejected, and if you are making a mistake on that, then the probability of that mistake is 10%. So that means if we are prepared to tolerate that in 10 out of 100 cases, we will go wrong, and we are okay with that, okay, then we can reject H naught. Remember that H naught is always formulated with the ultimate aim of rejecting it, demolishing H naught with the help of the data. Okay, and sorry, this sentence is not complete. So what does this mean again? So interpretation in the named entity identification situation is that suppose the named entity identifier tagger is actually doing random guessing, and if we reject H naught, then if we say that no, the named entity identifier tagger is not doing random guessing, but internally employing an algorithm that is better than random guessing, then what is the situation? As per the confidence interval, I am prepared to tolerate 10% type 1 error. And as per the data, the probability of going wrong with the stand that no, the named entity identifier tagger is better than a random guesser is at most 10%. Okay, because Z naught has entered into the critical region. Okay, so if you are prepared to tolerate 10% type 1 error, okay, error of rejecting the null hypothesis, then we can accept the statement that the named entity identifier is better than a random guesser. What about 95% confidence interval? Now Z observed is 1.98. Z critical is 1.65. Again, we have entered the rejection region, and H naught now can be again rejected. Okay, reject H naught and we accept HA. In other words, the data in conjunction with the confidence interval suggests that the named entity identifier tagger is doing better than random guessing. Okay, so we are trusting the named entity identifier tagger. And is this trust misplaced? Okay, is this trust misplaced? That is decided by the confidence interval we have chosen for ourselves. Now we take the situation where we cannot reject the hypothesis. Now Z naught is 1.98. We have got this from the data. Critical Z for 99% confidence interval is 2.33. Okay, so here the rejection region is much smaller. Critical region is more towards infinity. So value is higher. And we are prepared to tolerate much less error, only 1% error. So ZO does not enter the rejection region, and now H naught cannot be rejected. Okay, cannot be rejected. So on the basis of the data and confidence interval, we cannot rule out the possibility that the named entity identifier tagger is just doing random guessing. Okay, so if we are much less tolerant, we are not prepared to tolerate high level of error, then we cannot reject the null hypothesis based on the data. Okay, so since 32 errors have occurred out of 50, okay, 32 errors have occurred out of 50. On the face of it, the error is 65. The accuracy value is 64%. But if our acceptance level is very low, tolerance level is very low, okay, we can tolerate only 1% error. We can go wrong only in 1 out of 100 situations. Then only 64% accuracy is not enough for me to rule out the possibility that this named entity identifier is just doing random guessing. Okay, that is the consequence. I hope you have understood. Now, what does it mean? Which implication is correct? You see, depending on the confidence interval, we have rejected the hypothesis, or we have not been able to reject the hypothesis, depending on the confidence interval. Okay, so now what is the truth actually? Which implication is correct? So the answer is that all implications are correct. It depends on the tolerance level. Okay, that means what confidence interval we have chosen, how much type 1 error we are prepared to accept. So if we are prepared to accept only one error case out of 100, which is very stringent, we cannot reject the null hypothesis. Okay, we cannot say that the named entity identifier tagger is not doing random guessing. Internally, it has a very simple algorithm. Just tosses a coin and gives the tag of a name or no name. Okay, so if my error tolerance limit is very low, I cannot reject this hypothesis. Based on what? 64% accuracy. If I am prepared to tolerate 5 errors out of 100, then I am less stringent, and then I can reject the hypothesis. I can accept the statement that named entity identifier is doing better than random guessing. And if we become more flexible, if we are prepared to tolerate 10 errors out of 100, then all the better. Okay, it is a much looser situation, much more flexible situation. I am prepared to say that the named entity identifier is actually employing a good algorithm, which is much better than random guessing. Notice the role of 32 out of 50. Role of 32 out of 50. Everything is based on this 32 out of 50 or 64% surface level accuracy. Okay, and everything again, secondly, is dependent on the confidence interval we have chosen. So this, I think, you are appreciating that how much to trust the performance of a system, or any situation for that matter, where hypothesis building is informed, depends on how much error we are prepared to tolerate. What kind of error? Type 1 error. What is type 1 error? wrongly rejecting null hypothesis. What is null hypothesis? H0, which is formulated depending on the situation. So these are very important understandings which applies to our application of which pertains to our application of probability to machine learning situations. So let's make our context a bit broader and look at the field of natural language processing as such. So we know that our field has a fundamental framework, which is the pipeline. We start with morphology analysis on the words, do part of speech tagging, chunking, parsing, semantics, and discourse and coreference and pragmatics at the highest level. For example, emotion and sentiment analysis goes to a very high level of natural language processing. But the whole structure is built on many lower level tasks, namely morphology, part of speech tagging, chunking, and so on. Part of speech tagging, giving correct noun, verb, adjective, adverb, etc. tags on the word is a very fundamental task right in the beginning of the pipeline. If part of speech tagging is wrong, then the whole structure becomes shaky. Okay, the whole pipeline becomes shaky. The downstream application also becomes erroneous. Okay, so this is the NLP pipeline. And let us examine the question of hypothesis formation, hypothesis testing in the context of the NLP pipeline. Now, we take a practical situation. We are discussing sentiment analysis. Suppose there is an e-commerce company which has built a sentiment analyzer. Suppose Flipkart, Amazon, Big Basket, these are e-commerce companies. They have built a sentiment analyzer to track the customer sentiment. And customers give opinion publicly on the portal. The opinion of one customer can influence the opinion of maybe 10 other customers. And this can percolate and can exponentially propagate to build a massive opinion. So this kind of customer opinion has a big implication for the business. So if we do not detect the negative sentiment correctly, then the business can be ruined. Okay, so we have three kinds of sentiment: positive, negative, and neutral. All these sentiments have their own place, but in particular, I have to be careful about negative sentiment. If I do not track the negative sentiments and take steps to ameliorate this situation, then my business interest will be hampered. So in this context, we know the importance of false positives, false negatives, precision recall, F-score, etc., which are nitty-gritties or nuts and bolts of machine learning. So precision recall are very frequently employed in machine learning situation. And this diagram we have seen many times in NLP course and elsewhere in discussions is very helpful. So S1 is the obtained set, S2 is the actual set. Now S1 intersection S2 is the true positive. Okay, so these are instances which are given the positive level by the algorithm, and these are true positives. Okay, the set S2 is actual. Now S1 intersection S2 is true positive. S1 minus S1 intersection S2, that is S1, this dark region, okay, minus the intersection region, S1 minus the intersection region, which is this half moon, okay, on the left hand side. This is the false positive. The machine learning algorithm has labeled these instances as positive, but actually they're outside S2. That means they're actually negative instances. So these are falsely marked positive, therefore they're false positives. Similarly, S2 minus this intersection region, this half moon red region, this is the false negative region. Okay, false negative region. And what is the true negative? True negative is the whole universe minus the S1 minus S1 union S2. Okay, so S2. So this is the true negative region. Now, The precision is obtained by S1 intersection S2 divided by S1. Okay, the true positive divided by the size of S1, and recall is S1 intersection S2 divided by S2, which is actual. Okay, so you can also see that S1, this whole set S1, is nothing but the intersection region and the half moon region. So this is actually a true positive plus false positive. Okay, true positive plus false positive. So precision is true positive by true positive plus false positive, right? And similarly, recall is true positive by S2, which is true positive, uh, true, true, true positive plus false negative, right? Plus false negative. So this Venn diagram is very helpful for understanding precision and recall. And when we bring in probability, they can be very nicely mapped to the type 1 and type 2 errors. But let us do some qualitative analysis. E-commerce company has built a sentiment analyzer, okay, because it cannot track all the customer opinions. The volume is just too large. Now make mistake on of harming the business interest. So this is a more serious situation. Making mistake on positive sentiment can be economically wasteful and irritating for the customer. This is less serious. So we can have wrong palliative communication to the customer. We apologize for, and the customer will think, why am I getting this message? Okay, because it is a false, it is a mistake situation. We are making a mistake on the positive sentiment. When the sentiment was positive, we labeled this as negative. And therefore, we have sent an apology message to the customer, and the customer wonders why I am getting this message. But this is not very harmful. Okay, in the long run, it can be harmful. The customer may become suspicious of the intelligence of the company. But if I ignore the negative sentiment, class them as positive or neutral, then this is a much more serious concern. I lose business. Okay, so now you can see that for negative sentiment, negative sentiment, my test has to be more stringent. Okay, so negative sentiment for I would like to do. I like to adopt 99% confidence interval, 95% confidence interval. Okay, so if I want to be very strict on negative sentiment, okay, then what implication does it have on precision and recall? Think about that point. Okay, precision and recall is obtained by this Venn diagram: S1 intersection S2 divided by S1, S1 intersection S2 divided by S2. Now, if I have to be stringent with confidence interval 99%, all specifically on the negative sentiment side, okay, then how should precision and recall be formulated? And what is the relationship with type 1 and type 2 error? Okay, this is something we'll explore very carefully in the next lecture, the relationship between precision recall and type 1 and type 2 error when we bring in probability. So, so let us examine this question a little more qualitatively in terms of the company's management decisions. So we hire a data scientist. Okay, let's say Amazon, Flipkart, they hire a data scientist. And what is her responsibility? The data scientist has to formulate the right question as per the demands of the situation. She has to take care of the business interest, which is why the data scientist has been hired. Okay, data scientist is not doing programming. She is not a machine learning engineer, NLP researcher. No, she is not doing system building. Okay, what she is doing is she is analyzing data and taking care of the business interest. So she has been told that not detecting the negative sentiment can be quite risky and dangerous situation. So the data scientist has been asked to formulate the null hypothesis correctly by analyzing the problem situation, the business interest minutely. And she is asked, what really will be the null hypothesis? Okay, I have positive sentiment, negative sentiment. For the moment, let's say only positive and negative sentiment. no neutral class. Okay, customer opinions have sentiment, and negative sentiment has to be tracked properly. What should be an appropriate null hypothesis? This is a data science question. Can the machine learning researcher do it? Maybe, if he or she has good training in statistics and probability, and fix the confidence interval properly. And remember that sampling costs money. Okay, collecting a lot of customer opinion, processing it by various tools can be expensive. Okay, so this is how an NLP company would interact with a data scientist, and this will be the job of the data scientist. Okay, armed with the concepts of probability and statistics. So let me quickly take up another illustration, which is not NLP, but you have seen it before. The bottling of fluid situation. A factory has a machine that the factory claims dispenses 80 milliliter of fluid in a bottle. This needs to be tested. A sample of 40 bottles is taken. The average amount of fluid is 78 milliliter with standard deviation of 2.5. Verifies the factory's claim. So this is not an NLP situation, but has similarity. Okay, and there are consequences. If the claim is that every bottle has 80 milliliter of fluid, and actually the bottles are containing less than 80 milliliter, then the customers are cheated. And such customers, when they find out that they are getting cheated, they will move away from the company. So this will be a loss of the business, harmful. But there is an equivalent situation also. If we consistently fill more than 80 milliliter, then the company will eventually make loss. Okay, because the assumption is there is 80 milliliter, and that is the requirement. But if you always fill more fluid than 80 milliliter, then after some time it will be economically not viable. That is also a loss. Now you see, on both sides, positive error, negative error, both sides are harmful. Which kind of mistake is more harmful? That is a problem specific situation, and after analyzing this problem situation carefully, we would like to form the null hypothesis accordingly. Okay, so here also, as you know, once we formulate the null hypothesis and we have decided on the confidence interval, then that begins the process. Okay, and you can decide on a two-sided test, one-sided test. In this case, for example, we are not interested in not equal to case. Okay, no, we are interested in not equal to case. So the null hypothesis is equal to, and alternative hypothesis is not equal to. Okay, neither less than 80 nor more than 80 is acceptable to us considering the business situation. But if the business situation is that the customer should not feel cheated, then we'll adopt a one-sided test. Okay, and then of course the critical region will shift accordingly. So these are the nitty-gritties of hypothesis testing. Our next task will be to relate this with the machine learning situation, some NLP problem situation. This sentiment analysis situation is very nice. Similarly, if a doctor is detecting whether the patient has cancer or not, okay, there again false positive and false negative have different degrees of seriousness. If the patient actually has cancer, and we say by testing that he or she doesn't have cancer, that's a very dangerous situation. But if the patient doesn't have cancer and we say the patient has cancer, then it is very expensive for the patient, okay, unnecessarily. So both situations have seriousness with respect to mistake, but we have to appropriately form the hypothesis and decide the confidence interval accordingly, depending on the problem. Okay, so this is something, this is a skill that we have to learn as data scientist. Okay, so I'll stop here today and ask if there are any questions. Any questions? Am I audible?
Yes, sir.
I said visible. Okay. So any question from anybody? No? Okay. Okay, so if there are no questions, then we'll take up this precision recall and type 1, type 2 error question in the next class. And as you know, our information extraction 2 meeting will be at 4 o'clock today. The link has been shared by Kaveri. Okay, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.